Hello, welcome to section 4.8, where we are going to talk about complex numbers. So our goal today is to identify, graph, and perform operations with complex numbers and to find complex number solutions of quadratic equations. Back in section 4.7, we started to introduce the idea of the discriminant, and when the discriminant is negative, we discussed how there was no real solutions. But mathematicians weren't happy with that, so they came up with the imaginary unit system to identify these numbers. So we can take the square roots of negative numbers and use an imaginary unit to express that number. The idea was, um, it goes back to early times back in Greece, but it wasn't fully proven until the 1500s by an Italian mathematician named Raphael Bombelli came up with a method to identify these square roots of negatives. So the imaginary unit is a variable we can use to represent the imaginary set of numbers. So the imaginary unit is used to find the roots of negative numbers. Here's how the number I is represented. I is defined as the square root of -1. So the square root of -1 now becomes I. So anytime we have a negative number, we can always break it into factors of -1 and the given number. So also then I squared is equal to -1. And we also have some other definitions for I as we start to square it, take it to the fourth, take it to the sixth, so on. So our two main definitions that we are going to use today are that anytime we take the square root of -1, that gives us our imaginary unit I. And anytime we take I squared, that brings us back to the real number system of -1. So when we talked about square roots back in section 7, so for example, if we took the square root of 16, that would equal plus or minus 4. Now, if we take the square root of -16, this is now possible because we can think of the square root of -16 as the square root of -1 times the square root of 16, where square root of -1 is I, and the square root of 16 is 4, so now we get plus or minus 4I, and we're always going to write the I second, just like we do with all of our variables. So problem 1, how do we simplify a square root of a negative? So we're going to take the square root of -24, we'll think of it as the square root of -1, times the square root of 24, and then 24 is not a perfect square, but it does have perfect squares in it, so we'll take the square root of 4 times the square root of 6, and square root of 1 is I, square root of 4 is 2, so we'll have 2I roots of 6. And then there would be our simplified version of the square root of -24. Some new concepts. We defined imaginary number above. A complex number is a number that is written in a plus bi form, where a is the real number part and bi is the imaginary part. So we can take the real number part and imaginary part when we start to solve out using the complex number system. Pure imaginary number has no real part, just the bi part, so just the imaginary part. A complex number plane is an xy axis, so something we're used to seeing, where we can graph complex number. X axis represents the real axis, and then y represents the imaginary axis. And then the absolute value of a complex number, just like absolute value of a real number, is the number's distance. But here we're going to look at the number's distance from the origin, because now we have a two-dimensional plot that we're going to be making, and then we can find its distance. And we're going to lean on another old mathematician, Pythagoras, to find the absolute value, but we're going to use that little formula there, and we'll talk about why we use that in just a second. We take the square root of a squared plus b squared to find the absolute value. So we'll start by graphing our complex numbers. So we'll graph the 1 and the -3, the a and the b, based on the a and b axis on our coordinate plane. So we're kind of thinking of it as the number, or the coordinates 1, -3. So 1 would be 1 to the right, and then -3 is going to be down 3. So there's a complex number a1 minus 3i. The absolute value then is this distance back to the origin. When I have a diagonal on the coordinate plane, I cannot for sure calculate that distance because I'm cutting across those squares. But any diagonal on the coordinate plane you can complete to make a triangle. And then the special thing about this triangle is it is a right triangle. And one of the sides is 1, the other side is 3. And sorry about my pen, it's not really showing up that great, but we have a side of 1 and a side of 3. The missing side then is over here, which we have called the hypotenuse in the past. So we're going to use the Pythagorean theorem to find that missing side, that third side, and we'll write out the Pythagorean theorem, but then we're going to show how this formula up here really is all that we need to calculate that distance. So at this point, I've set up the Pythagorean theorem. To undo a square, I'm going to square root, which would cause me to square root both sides to balance my equation. So really all I'm doing is the square root of 1 squared plus 3 squared, which ends up being the square root of 10. And I'd look to simplify that, I can't. So there's going to be my distance. Now maybe you're wondering, whoa, wait a second, Mr. Rengel. The 3 was -3, so why did you use a 3? Well, in the Pythagorean theorem, it doesn't matter because if you square a negative number, square of -3 is still going to equal a positive 9. So I'm just using the absolute value of that distance in my calculation. But overall, all we need is the square root of a squared plus b squared, and we can find that distance. Part 2, I'll take -4, 1, so I'll go -4, up 1. Now, calculating the absolute value, I'll take -4 squared, or I could just use 4 squared plus 1 squared. And either way, I'm going to get the square root of 17. So there's going to be my absolute value distance from this point back to the origin. Next, we can add or subtract these complex numbers. So we're going to take, in this first situation, we're going to add 2 plus I plus -3 plus 3i. So both these are complex numbers because they have a real and imaginary part. And when we're adding them, we can only add the real parts together and the imaginary parts. So I'm just going to combine terms. 2 -3 is -1. I plus 3i is going to be 4i. So there's going to be my addition. Next problem, we got a 5 plus 5, which is 10. I plus -I is 0i, so this one changes to a real number. C, I'm going to have a -6 minus 4, so be careful. You're at -6. You take 4 more away, you're at -10. -2 minus 2, it's not going to be 0. We're subtracting 2 from -2, so we're going to be down to -4i. So to add or subtract, we can just combine the reals together, combine the imaginary parts together. Now let's take a look at multiplying. So we're going to use some of the same skills we've always used with multiplying numbers, binomials, when we get into variables, same type of skill set. So here we're going to multiply -I by 4 minus 8i, which is going to cause us to use the distributive property. So I'm going to go -4i, and then I'm going to go -I times -8i, which is going to be plus 8i squared. Now we're not quite done yet because we do have to apply one of the rules of the imaginary units. This piece right here, we can't forget. Anytime you have a I to an even power, it can simplify. That's going to equal -1. So really this 8 now becomes -8. So I'm going to have -4i minus 8. From there, I still have to put it in a plus bi form, so I'm going to have -8 minus 4i. So anytime we have an I raised to an even power, that is actually a real number, so we have to change that back. So be aware, anytime you have that I raised to a 2, to a 4, to a 6, you can change that back to a real number. Part B is probably looking familiar to us. We have two binomials, which is going to cause us to use FOIL. So we're going to FOIL this out. So 5 times -4 is going to be -20. Outsides, 5 times -3i is going to be -15i. Inside's negative times a negative, which is going to be positive, and then that's going to be a 28i. And negative 7 times negative 3 is positive 21, and then the I times the I will give us I squared. So here we have a term that has the I squared, so we have to recall this is really a negative 1. It's kind of like a secret in hiding. There's that negative 1, so that's going to mean this really is the number negative 21. So as I can continue to simplify, I'm going to think of that as a negative 21. So now we're going to have a negative 41 combining with that negative 20. And then negative 15 plus 28 is positive 13i. So there would be our result. I want you to try one additional problem on your own. So you can pause the video right here and try to multiply out those two binomials using the FOIL method. And you should see something interesting happening as you start to multiply this one out. So when you unpause your video, I will have the answer and we'll talk about it. After doing FOIL, we should see that our O and our I are going to become negative 6 and positive 6, which add a negative 6, positive 6, that's going to equal 0. So then we're left with that 4 minus 9i squared, but we see that I squared, that's really a negative 1, so a negative 9 times that negative 1 there is really a positive 9, so we get 13. So all this up here is equal to 13. And if you look at it a little closer, really all you're doing is you're taking 2 squared plus 3 squared. And where does that come from? That's just taking the a of your your complex number squared plus the b of your complex number, and that's giving us that answer of 13. So who knew? That's another way that you can get to 13 by multiplying those two complex numbers. Those special pairs of complex numbers are called complex conjugates. So complex conjugates are complex numbers in the form a plus bi and a minus bi. And whenever you multiply out complex conjugates, all you're doing is you're taking the a part squared plus the b part squared to get your result. And the other unique thing about complex conjugates is when you multiply complex conjugates, they're always equal to a real number. So it's a way that we can change a complex number back to a real number. So the reason we would need to use this is anytime we have a quotient, which is dividing, it is impossible to divide by an imaginary number because it is such a unique number. We don't really know what the number is, so we can't divide by something we don't know, just like we can't really divide by 0 because that doesn't really work either. So we have to change the divisor, which is the number in the denominator. We have to change that back to a real number. So we're going to use a couple strategies, including complex conjugates, to get our divisor back to a real number. So we'll use complex conjugates in B and C because those are binomial. Those are complex numbers. If we just have a pure imaginary number, we have other methods, thinking about how the I squared works and getting that back to a real number to be able to simplify this. For part A, then, I cannot divide by a 4i because it's imaginary. But when you have a pure imaginary number, if we just multiply 4i by I, it becomes 4i squared. And we should know by now that I squared is equal to, yes, negative 1. Now in our numerator, we're going to multiply by I as well. We have to balance our fraction, multiply both numbers by I. So up in the numerator, I'll have a little distributive property. We'll have 2i plus 3i squared. And in our denominator, we'll now have a 4i squared. And now we'll continue to simplify this problem. So remember now, I squared is negative 1, so really this 3i squared is negative 3 plus 2i. Just putting that back in a plus bi form, and then 4i squared is really negative 4. The next thing we'd look at is if either of these numbers are divisible by negative 4, and 2 and 4 both have a common factor. So we're going to continue to simplify this. Negative 3 divided by negative 4 is 3/4. And then over here, we've got a 2 divided by negative 4, which I got a little ahead of myself. I shouldn't have put that plus sign. That's going to be 3/4 minus, because I'm doing a positive 2, negative 4, minus 1/2 I. So there would be my complex number simplified. 3/4 minus 1/2 I. So because I could not divide by that 4i, we had to change them back to some real numbers. Now we're set. Now as we get to part B, we have a complex number in a plus bi form. Now we can't do the little trick of multiplying by I, because if I multiply by I would be required to distribute, which would make it 8i, and I'm still dealing with a imaginary number, so it's not going to really do anything for me. So here's where we have to use our complex conjugates. So if you have an 8 plus I, we can multiply using the same 8 and I, multiply by 8 minus I. And then we have to do the same thing in our numerator. We're going to multiply by 8 minus I. So the next thing we'll do is we'll do a little multiplying. Now, your conjugates, remember, we can use this little trick. All you have to do is take your a squared, which will be 64, plus your b squared, which is a 1, 64 plus 1, so your denominator is going to be 65. Now we simplify our numerator, which is going to cause us to distribute this 7i to both the 8 and the negative I, so I'll get 56i, and then 7i times negative I will be negative 7i squared. Then to finish up, we'll take that negative 7i squared, let's get that back to a real number, so I squared is negative 1, negative 1 times negative 7 is positive 7, so we'll have 7 plus 56i over 65. And then I look, 7 and 65 don't have any common factors, 56 and 65 don't, so that is as simplified as I can get. So looking down at C, I'm running out a little bit of room here, but we're going to multiply both our numerator and denominator by the conjugate, which is 3 plus 2i. Okay, and then I'm going to pause here, and you can try it on your own, or I will come back and we'll work through the rest of the problem. So we'll start with the denominator. We have a 3 minus 2i times 3 plus 2i, which is the conjugate. So we'll take 3 squared plus 2 squared, which gives us 13. And then our numerator, we're going to FOIL out, and we'll get the result shown. Now we can combine any like terms. 15 will combine. This is negative 4. Remember, that makes 11. 10 and 6 makes 16. So we'll have 11 plus 16i over 13. And again, 11 and 13, 16 and 13 don't have any common factors because 13 is prime. So there's our final result. So a little trick that we can do to change complex numbers back to imaginary numbers, or back to real numbers, we can use these complex conjugates. The last thing we can do with imaginary numbers is we can now find solutions to those graphs that do not cross the x-axis. So those ones where the discriminant was negative back in section 7, we can now find the imaginary solution. So number 6, we look at 3x squared plus 12 equals 0. We only have 2 terms. We do not have an x term, so we can solve using square roots. We'll get 3x squared is going to equal negative 12. And then we'll divide both sides by 3. We'll get x squared is equal to negative 4. And lastly, we'll take the roots. Square root of negative 4 is going to equal plus or minus 2i. So if we have just those an x squared, we can get the x squared isolated using algebra, and then our imaginary solution would be plus or minus 2i. In problem 7, we have 3 terms, including that x term, that linear term. So we have a negative x squared plus 4x minus 5 equals 0. So one thing to know about these quadratics where we're going to get imaginary solutions as they do not factor. So we have to use the quadratic formula. So we'll pull out, there's our A term, -1, our B term is 4, our C term is -5. So we'll put that into the quadratic formula. In case you forgot what the quadratic formula was, there it is right there. Now we'll get our B term put in, our A term, and our C term, and we'll start to solve it out. So we'll start by working under this root and figuring out what that is, and you'll see that it is going to be negative. So similar to in section 7, that discriminant is negative. We used to say, or we did say, it's got no real solutions, but here we're going to find 2 imaginary solutions. So we'll find the discriminant, which is going to end up being 16 minus 20, which when we do 16 take away 20 brings us to -4. So here's where we have that negative discriminant, no real solutions, but no worries. The imaginary numbers are here to the rescue. So we can take the square root of -4 now. It's going to be 2i, and that's all over -2. And then we look, do 4 and 2 have any common factors with -2? Sure do. So -4 divided by -2 is 2. And then plus or minus I, it doesn't matter. When you do 2 divided by 2, you're just going to simplify that 2 as a common factor. So our final result is going to be 2 plus or minus I. So if we can, we're going to take and find common factors between our numerators, denominators, like we found in section 7. That's not always going to be the case, but if we can, we will simplify as much as we can to get our final result. Well, thanks for joining. That concludes lesson 4.8, an introduction to complex numbers. Again, thanks for joining, and we'll see you next time.